In this video, I want to have a look at a couple of facts about polynomials that help us to understand them a little bit better and help us to solve problems. So our first one says if a polynomial p of x has k distinct zeros, and those zeros are a1, a2, a3, all the way up to ak, then that means that x minus a1, x minus a2, x minus a3, multiplied all the way up to x minus ak, then that whole thing is going to be a factor of px, so a factor of that original polynomial. If we look at it a little bit closer, if we know that a1 is a zero of that polynomial, then that means, so if a1 is a zero, then that means that x minus a1 is a factor. Same thing goes for a2. If a2 is a zero, then x minus a2 is a factor. And that works all the way up for all of the factors. So if a to the k is a zero, then x minus a to the k is also a factor. So if all of these things are factors, then if we multiply all of the factors together, the result is also a factor of our polynomial. Our second property says that if a polynomial p of x is of degree n and it has n distinct zeros, which are a1, a2, a3, all the way up to an, then our polynomial can be written as p of n, which is a constant, multiplied by all of those factors. So we already said in the last one that if these are our zeros, then that means that this whole expression here is a factor of our polynomial. So that means we could write p of x equal to x minus a1, x minus a2, all the way up to x minus an, multiplied by q of x. So there's no remainder because we know that this is a factor. But if we've got n distinct real roots, so there's going to be n lots of these brackets, and our polynomial is of degree n, that means that this quotient has to be of degree 0. It has to be a constant term, because we can't have another x here, or it would make it a degree n plus 1 polynomial. So if that's a constant term, then we can write it just as Pn. So it's a constant multiplied by all of those factors. Our third one says that a polynomial of degree n cannot have more than n distinct real zeros. So if we use the notation we were using earlier, if we had a zero at a1, then that would mean x minus a1 was a factor, and we could do that all the way down to an, so x minus a to the n is a factor as well. So we're saying degree n, if a polynomial of degree n cannot have more than n distinct real zeros. Let's pretend it does for a second. So let's keep going to n plus 1. So we've got x minus an plus 1. And we could keep going, but let's just use this one for now. If all of these are factors, then we could write p of x equal to x minus a1, x minus a2, all the way up to x minus a to the n plus 1. And because all of this is going to be a factor of the original, we'll multiply it by the quotient. Now, even if this quotient is a constant term, if we were to expand this whole thing out, we would end up with an x to the power of n plus 1, giving us a polynomial of degree n plus 1, but that doesn't make sense if our polynomial is only of degree n. So we can't have more distinct real zeros than the degree. Now, the only exception to that rule is if we have a polynomial of degree n with more than n distinct real zeros, then it is the zero polynomial. So it's just the polynomial p of x equals 0. Our next one says if two polynomials of degree n are equal for more than n distinct real values of x, then the coefficients of the like powers of x are equal. So translating that, if we have a polynomial, so a0 plus a1x plus a2x squared plus all the way up to an x to the power of n, if that is exactly equal to b0 plus b1x plus b2x squared plus all the way up to bnx to the n, then that means that our coefficients have to match up. So our constant terms a0 and b0 are equal. The coefficients of x, so a1 and b1, are equal, all the way up to coefficients of x to the n, so a to the n plus bn are equal as well. Our last one says, if x minus a is a factor of the polynomial p of x, then a is a factor of the constant term of the polynomial. So this really helps us when we're solving questions like we were doing in our factor theorem video, when we were given a polynomial, so something like x to the power of 4 plus 2x cubed minus x squared plus 24. And we were asked to write that as a product of its linear factors. And we were going through and testing, so we were like P1, P2, and seeing which of these came out to be factors. Now, sometimes it can be tricky to figure out which values to test, but this tells us that the numbers we need to test always have to be factors of that constant term. So we would only bother testing numbers if they were factors of 24 in this case. All right, so those are some properties of polynomials that come in handy.